Hi, so far we've looked at undamped vibration, things like simple harmonic motion of a mass on a spring or a pendulum. And this kind of system doesn't give us our ideal response. We don't want something to keep on oscillating like that. We want to try and steady any vibration down. And to do this, we introduce a damper. So I've got a graphic here which shows kind of the response of a typical for a car suspension, for instance. We've got a spring and a mass, but we've introduced now like an oil-filled dashpot which acts as a damper, and that absorbs some of the energy that's in the system. It dampens down the amplitude of oscillation, and of course all that energy really goes into generating heat within the damper. And we need to make sure, if we're designing systems, that we get the balance of the spring and the damping right to give us the response that we want. And I've just got quite an extreme example here of where we really do need to get a system response correct in order that we don't cause any injury, in this case to this sit skier. Needed to be absorbed by the spring and shock system within that sit ski. So what do we have then in our system? Then here we've got an example of car suspension, and we have the three components, which is our mass, which is generally the system itself, and we support that on a spring. That'll have a stiffness K, and now we have a damper, and that has a damping coefficient which we term C. This is how we would normally represent all of our systems. We just kind of represent it in a diagram like this, which shows the three components. And here we just have some typical examples of where we will see that spring and damper working together in order to prevent or to reduce the amount of vibration or oscillation, be it for photography, where any vibration might cause a blurry image, to things like safety systems on bikes to stop the steering oscillating, or on caravans and trailers, and down to simple things like the closure that you'll find on many doors, especially fire doors. And in this system here that closes the door, it has a spring and a damper system. Let's take a look at the forces that are involved in our system. We've got the three components, the mass, spring and damper. So let's run through those in turn. What do we know about mass then when it's moving? Well, if it's moving, or even if it's stationary, it has a resistance to change its velocity, and that's its inertia. And that's the same whether it's a linear system or if it's an angular or rotary system. And if it's moving, then the mass times velocity gives it some momentum. So therefore, in order to control the mass, then the mass relates to acceleration. So the force relates to mx double dot, or F equals ma. Looking at our spring in a system then, what do we know about springs? Well, if we compress them, then they store that energy, and if we release the external load, then the spring will return back to its original length, so it releases that energy again. It stores the energy and then releases it. And we need to apply a force in order to change the length of a spring, but it doesn't matter how fast we compress or extend a spring, the same force is needed no matter what. So the force within a spring relates purely to the distance that it's extended. So in this case, F equals kx. The final component then in our system are the dampers. And what do we know about dampers then? Well, we need a force to change the length of a damper. And in doing so, that will absorb energy. The energy that we put into that system will effectively be converted to heat through friction of the oil within the damper itself. And the force that we need to compress the damper will change depending on the speed of which we try and compress it. So if we go slowly, it doesn't take much force, but if we try and compress it really quickly, then it provides a lot of resistive force. So therefore, our dampers in the system relate to the velocity. And as I mentioned earlier, C in this equation is the damping coefficient. So the force equals C multiplied by x dot. Here we have an illustration of 3 different dampers, and it's to try and illustrate the damping coefficient. And we can make a damper very simply by putting a piston in a cylinder, and then if you put a hole in that system, then it'll allow the oil to pass through if we push on one end or the other. And you can see here on the left hand side with a single hole, then it provides quite a lot of resistance, so it goes slowly. And moving over to the right hand side where there's lots of holes in the piston, the oil can move relatively easily through all of those holes, so it doesn't provide so much resistance and therefore acts faster. Let's see how our system could respond then if we give it some kind of disturbance. So if we look at a system with no damping, then it's like we've seen in previous weeks, we will get simple harmonic motion. But if we introduce a little bit of damping, then as we would expect, we'll reduce the amplitude with successive oscillations until the system settles at the neutral position. And if we increase that damping then even further, we'll get to a point where we've got lots of damping and we can get a very sluggish response. And you can see here we can damp it so much that we don't get any oscillation at all. But this kind of system is really slow and it's not very helpful to us in most of our dynamic situations. So what we need to do is try and balance the system response against the type of disturbance that we're going to get. And what we'll look at on the next slide is how we can classify these kinds of response. So if we've got a little bit of oscillation, then we get an overshoot from the neutral position, and we will call that system an underdamped system. If we increase the damping to the point where we get this sluggish response, there's no overshoot, we would call that an overdamped system. And we can get a balance in between those where we get to the neutral position without overshoot, but in the fastest possible time. And if we do that, then we call that system critically damped. So critically damped is the quickest time that the system can respond, but without any overshoot. An important term in classifying how our system is going to respond is a thing called the damping ratio, and we give that the Greek letter zeta. And the damping ratio is simply the amount of damping in our system divided by the amount of damping needed to give us a critical response. So if we look at the system we've got here, the yellow line, we've got an oscillation, so we know that it's underdamped. And if we have an underdamped system, then our zeta will be less than 1. If we go to the other extreme where we've got a really sluggish system with no overshoot, then our zeta value will be greater than 1. And if we have a critically damped system, then our zeta value will be equal to 1. Right, there's quite a lot going on this slide, but I'll just like to try and take you through it. If we look at the graph on the left hand side here, it shows 2 responses. One is the orange line, and that's our undamped response, and that would give us our natural frequency, that will be omega n. And the blue line shows the response with a little bit of damping in the system, and we term that our damped natural frequency, and we give it the term omega d. And we've already seen how the damping in the system can reduce the amplitude of oscillation as we can see here on the graph each time. But what it also does, it slows the system down slightly as well, which probably is obvious, maybe, I don't know. But if we move over to the left hand side here, sorry, the right hand side, then I've kind of zoomed in just on this point here, and you can see that here in this response that the damped frequency, the blue line, is slightly slower than the orange line. So the damping in our system has two effects. It reduces the amplitude of oscillation, and it also slows the system down slightly. And down at the bottom of the slide here, then we've got some equations. I'm not going to derive any of these, we're just going to take these as fact, and we're going to use them in trying to determine how our systems might behave. So if we kind of go from left to right, then the equation here on the left relates to the damped frequency, to the natural frequency, and the damping ratio. So our frequency of damped oscillation, omega d, equals our natural frequency, omega n, multiplied by the square root of 1 minus zeta squared. And next to that then, here we have a relationship for zeta. So zeta, our damping ratio, equals our damping coefficient in our system divided by twice the natural frequency multiplied by the mass in the system. And then finally here over on the right hand side, all I've done is rearrange that equation so that we make our damping coefficient the subject of the equation. So what I think we should do now then is just run through a few examples just to use these equations and familiarize ourselves with looking at the amount of damping in a system and how that might change the response of that system. I'm just going to go through 3 examples then, and here in our first example we have a suspension system, and we've been asked to find the natural frequency of the system and the damped frequency of the system. And what have we got? We've got 12 kilogram mass, a stiffness of 400 Newton per meter, and a damping coefficient of 70 Newton seconds per meter. So we've got all we need really, first of all, to find the natural frequency, and then if we can calculate the damping ratio, we'll be able to work out then what the damped frequency is. So I'll just go on to a blank slide and run through that then. So what do we know? We know from previous weeks that our natural frequency is root k over m, and we've got those terms. So our natural frequency is going to be the square root of the spring stiffness, which is 400 over 20, and that gives me 5.77, and remember that will be in radians per second. And remember on one of the previous slides we have a term for zeta, which is our damping coefficient divided by 2 times by our natural frequency times by m. So we were given those terms. We've got 70 for C, 2. We've now worked out the natural frequency at 5.77, and the mass in the system was 20 kilograms. And that gives me a damping ratio of 0.5. So what does this tell us? This tells us that it's an underdamped system, and our system response then is going to be like this, isn't it? Where we get oscillation, but it will die away. And what frequency then will that oscillate at? Then we can find that out. We know that our frequency of damped oscillation is our natural frequency multiplied by the square root of 1 minus zeta squared. So that's going to equal 5.77 multiplied by 1 minus 0.5 squared. So frequency of damped oscillation is going to be, I worked that out to be 4.98 radians per second. And as you'd expect, this omega D value should always be less than your omega N value because it's slowing the system down. So if you find that this omega D here is actually, you calculate an answer which is greater than your omega N, then you've obviously done something wrong. So we'll just then move on to another example. In example 2 here, then we're asked to find out what the damping ratio is and the damping coefficient for the system. And the system has been tested and it's been measured to have a damped frequency of oscillation of 5 Hertz. And that's something that you could easily do. If you take a system, you could even use your mobile phone with an app, and you can put a disturbance on the system and then measure how it responds, and that will give you the frequency of damped oscillation. So in this case, we don't know what our damping coefficient is, but we do know what the frequency of damped oscillation is, and we know something about the system. We can work out the natural frequency from the mass in the system here, 8, and the spring stiffness, 15. So we'll just go on to the next slide and do the calculations. Where do we start then? Well, let's start by working out what the natural frequency is. So our natural frequency, omega N, is going to equal root K over M, which is going to equal the root of, and in this case the spring stiffness was 15 kilonewtons per meter, so it's 15 times by 10 to the 3 over the mass, which was 8 kilograms. So I work that out to be 43.5 radians per second. It's always worth checking my calculations because I do make the odd mistake. And now we also know that our frequency, and I'm using F here for our damped oscillation because we were given that in Hertz. Oops, can I just move that out yet? Equaled 5 Hertz. So then, therefore, our frequency in radians per second will be 5 Hertz times by 2 pi, which gives me 31.4 radians per second. And as I mentioned on the last slide, we're looking for this to be a lower value than that because the damped oscillation is slower than the natural frequency. Right, and we need to find out, what do we need to find out? We need to find out the damping ratio. So we know then that our damped oscillation equals our omega N multiplied by 1 minus zeta squared root. So in this equation then, we've just calculated out both of these values, so therefore we could rearrange for zeta. So we will get, if we take omega N across, so we're going to have, eventually zeta is going to be omega N over omega D. If we square both sides, so that will be squared, and then we take 1, so it's going to be minus 1, and that's going to be equal to zeta squared. So then if we square root zeta on that side, so we'll get the square root of all of that equals zeta. Okay, so therefore our zeta value is going to equal square root of 43.5 over 31.4 squared minus 1, and I calculate that out to be 0.69. so again we've got an underdamped system there. And then finally, if we use that third equation, we know that our damping coefficient equals zeta times by 2 times by omega n times by the mass, which equals 0.69 times by 2 times by 43.5, and the mass in the system is 8 kilograms. So our damping coefficient I calculate out to be 477, and that's in Newton seconds per meter. So our answers for this one, that's our damping coefficient, and our damping ratio is 0.69. And I guess we could just draw a little graph of that again. It's going to give us a response, which is going to be like that. Okay, on to the third and final example in this presentation. Here we've got the suspension on a car. So the total mass of the car is 1800 kilograms, and it's designed to have a damped frequency of 2 Hertz and a damping ratio of 0.4. So again, an underdamped system. And we need to determine what spring stiffness we need, and also what damping coefficient we need to give us that kind of response. So we need to find out C and we need to find out K. So where do we start? Well, first of all, I'm assuming that there's 4 wheels, so therefore I'm going to just do a very simple assumption and say, well, each wheel takes a quarter of the mass. So the mass on each suspension unit will be 450 kilograms. We know that the damped frequency needs to be 2 Hertz, and we know the damping ratio, so we can probably rearrange the damped oscillation equation to give us our natural frequency, and then we can probably use that then to calculate out the spring stiffness, and then finally the damping coefficient. So let's move on to the next slide and see how we do. All right, so we have a, I'll get the right pen colour, our frequency in Hertz for our damped oscillation was 2. So our omega d then is going to equal 2 times by 2 pi, which gives me 12.57 radians per second. Okay, and we know that omega d equals omega n root 1 minus zeta squared. So in this equation, we know what have we been to, we know this, yes. So we know the damping ratio has got to be 0.4, and we know this one we've just calculated, so we can work out what our natural frequency is. So our omega n is going to equal then our omega d over the square root of 1 minus zeta squared, which equals 12.57 over 1 minus, and the damping ratio is 0.4. So my omega n I calculate out to be 13.71, and again this is greater than my damped frequency, so I should be on the right lines. If it wasn't, if it was less, then I'd be worried. We should now then be able to find out what the spring stiffness is, because we know that our natural frequency is root k over m, and here we know what m is, and we know what omega n is now. Missed out with little equal signs there. So we should be able to rearrange for k. So therefore k is going to equal omega n squared multiplied by m, which equals 13.71 squared times by the mass, which we said was a quarter of the mass of the car, 450. So my k value I get to be 84.6, and that's to the 10 to the 3, so it's kilonewtons per meter. So there's my spring stiffness that I need. And remember then we can also say C equals 2 omega n zeta. I might not always put them in the same order, but it's the same equation. So our C value then is 2 times by 13.71 times by the mass, 450, times by my zeta value, which we said we wanted to get 0.4. So my C value I get as 4.93 kilonewton seconds per meter. So there we have it. So there's a little bit more work involved in that one. We had to recognize the different equations we're going to use and how we're going to rearrange those to find out the components of the system that we wanted to find. So that's all for this week. In the next lecture we're going to then look at the equations of motion for this system when we've introduced damping and how we might be able to then work out the accelerations, velocities and displacements. So that's all for now. Do go through the tutorial sheet, make sure that you're familiar and can do all the questions on this week's tutorial sheet. Thank you.